Welcome to my series of questions on AI and machine learning, and this is my questions on, that is, probability, Bayes networks and those things. So let us see. The Bayesian network gives, first question, a complete description of the problem, partial description of the domain, a complete description of the domain, and none of the above. Bayesian network, it gives all the dependencies, it gives all the variables, it gives all the factors. So a complete description of the problem or domain actually, it's a complete description of the domain, that in which situation we are working. So answer is a complete description of the domain. Why? A Bayesian network is a probabilistic graphical model that represents a set of variables and their conditional dependencies. It gives both a set of variables and their conditional dependencies on each other using a directed acyclic graph. Here this is important. Bayesian networks uses a directed acyclic graph, not a cyclic graph. You will not find a cycle in that one. It's the acyclic graph. It gives a complete description of the domain. Now this question is a bouncer. Let us face it, because such type of questions are going to come in GATE and we have to be prepared for these questions also. A patient goes to the doctor for a medical condition. The doctor suspects that 3 diseases as the cause of the condition. He goes with some medical condition. Now doctor suspects 3 diseases. The 3 diseases are D1, D2 and D3, which are marginally independent. Marginally means not unconditionally, independently. Okay. Independent from each other. D1, D2, D3 are not related to each other. Okay. There are 4 symptoms, S1, S2, S3, S4, which the doctor wants to check for presence in order. वो 4 तरह के टेस्ट कराएगा, एक्सरे कराएगा, अल्ट्रासोनिक कराएगा, कुछ कराएगा. Presence in order to find the most probable cause of the condition, which disease is there. The symptoms are conditionally dependent to the 3 diseases as follows. S1 depends only on D1. Means if disease 1 is there, then symptom S1 shall come. S2 depends on D1 and D2. Means if D1 and D2 any disease happens, S2 will come. If both happens, again S2 will come. And S3 depends on D1 and D3. If these diseases are there, then S3 will also happen, and S4 depends only on D3. Okay, so symptoms depend like this. Now assume all random variables are Boolean, they are either true or false. What is the number of independent parameters that's required to describe the following joint distribution? Joint distribution is very important in Bayesian networks. You can derive all the information, you can do all types of inference, approximate inference, and exact inference using this joint distribution. So joint distribution formula is given. Probability of D1, D2, D3, S1, S2, S3, S4 is probability of D1, probability of D2, probability of D3. Since they are independent, then probability of S1 over D1, probability of S2 over D1, D2, probability of S3 over D1, D3. Now the question is, what is the number of independent parameters that's required to describe the following joint? This is the joint distribution. How many parameters are required to describe it? 10 parameters or 15 parameters or 20 parameters or 127 parameters? How many parameters are required? So how to solve this thing? You can see answer is B, that was 15 parameters. How? Explanation. The number of independent parameters needed to describe each conditional probability distribution is tabulated here. See, this is the CPT, conditional probability table. Any Bayesian network consists of 2 things. One is the graph and another is CPT, conditional probability table. This is very much required for a Bayesian network. So this is the CPT. probability of D1, PD1, number of independent parameters 1. It's independent, only 1 is required. Probability of D2 again 1, probability of D3 again 1. So 3 diseases, 1 parameters will be required. Probability of S1 over D1. Probability of conditional probability of S1 over D1. Here 2 parameters are required, S1 also and D1 also. Then probability of S2 over D1 D2. Now D1 D2 and their combinations. So there will be actually 4 parameters, independent parameters. Both wrong or both right, or one right, other, or D1 right, D2 wrong, or D2 right, D1 wrong, like that. So D1 D2 combinations. So there, since there are 2 parameters, 2 to the power 2 combinations 4. Similarly D1 D3 combinations 4. It may be that why 4 are there, like that S3 symptom is coming. Now there may be disease D1, there may be disease D3, there may be both diseases, or there may not be any disease. Still that symptom may come. Probability is there. So that's why 4 parameters are there. Then probability of S4 over D3, again 2 parameters. If you count all these, 1, 1, 2, 1, 3, 2, 5, 4, 9, 4, 13, 2, 15. So total of independent parameters is 15. That's how it's being calculated. Which of the following is false? Variable elimination is an exact inference algorithm that can be used both for discrete and continuous variables under appropriate assumptions. Variable elimination, a method to get information from the Bayesian network. In variable elimination, the elimination, this is of course right. Variable elimination is an exact inference algorithm, yes, which can be used both for discrete and continuous variables, yes. So this is correct. B is in variable elimination, the elimination ordering can greatly affect the computational complexity, yes. Variable ordering is very important. Now C, in likelihood weighting sampling, the evidence variables are all taken into account by the sampling distribution. No, that's not wrong, because in likelihood weighting sampling, we take the evidences which are most likely. Those variables are considered. And D is Gibbs sampling settles into a dynamic equilibrium in which the long run fraction of time spent in each state is exactly proportional to its posterior probability. Very true. So C is false. C is the wrong statement. So it's our choice here. Answer is C. So how does likelihood weighting works? Likelihood weighting generates only events that are consistent with the evidence E and thus avoids the inefficiency of rejection sampling. It's a particular instance of the general statistical technique of importance sampling tailored for inference in Bayesian networks. Likelihood weighting fixes the values for the evidence variables E and samples only the non-evidence variables, not all the variables. This guarantees that each event generated is consistent with the evidence. Not all events are equal, however, before tallying the counts in the distribution for the query variable, each event is weighted by the likelihood that the event accords to the evidence, as measured by the product of the conditional probabilities for each evidence variable, given its parents. So, intuitively, events in which the actual evidence appears unlikely should be given less weight. So, that's the thing. Now, fourth question, a very standard question I got from Stanford papers. True or false? Assume the Bayes net from class is prefect of the word. Assume that this is representing the word. Stomach bug leads to vomit also and fever also, and flu also leads to fever and cough. In COVID situation, this is a very relevant question. Now you know that you don't have a stomach bug. ये हमें पता है कि मेरे को स्टमक बग तो नहीं है. Now if you were to vomit, अगर उल्टी आ रही है would that information change the probability that you had a fever? Fever is there. But here you see, vomit is independent of fever. There is no connection between them. So, you know that you don't have a stomach bug. If you were to vomit, would your information change the probability of fever? No. The two variables are conditionally independent, vomit and fever. That's why it will not change. If I know that I don't have a stomach bug, if you were to vomit, agar vomit ho raha hai, would your information change the probability that you had a fever? No. Vomit has nothing to do with having a fever, since there is no conditional dependency on that one. That's why the statement is false. How the Bayesian network can be used to answer any query? How the Bayesian network is so useful thing in handling uncertainty. Full distribution, joint distribution, partial distribution, all of them mentioned. Joint distribution is the key. We derive information from Bayesian networks through this joint distribution. So that's the answer. If a Bayesian network is representation of the joint distribution, then it can solve any query by summing all the relevant joint entries. That's how it works. Now, how the compactness of the Bayesian network can be described? What is the structure of Bayesian network? Whether it's locally structured or fully structured or partially structured, all of them mentioned. So this is Bayesian network is locally structured. Answer is A. The compactness of the Bayesian network is an example of a very general property of a locally structured system. Bayesian network is a locally structured system. That's how Markov chain and Markov blanket, they say that that particular node is only dependent on its children and parents of its children, its parents. Only these three things. So it's a local affair. What is the consequence between a node and its predecessors while creating Bayesian network? So of course, they are conditionally dependent, functionally dependent, dependent, conditionally independent, both conditionally dependent and dependent. So answer is C, conditionally independent. What is the consequence between a node and its predecessors while creating Bayesian network? So node is not any way affected by its predecessors. That's what it's trying to say. Once arrow has come down, so it's conditionally independent. The semantics to derive a method for constructing Bayesian networks were led to the consequence that a node can be conditionally independent of its predecessors. Predecessor से मतलब नहीं होता है, successor से मतलब होता है. So like this, you see, the node where the arc originates is called the parent, while the node where the arc ends is called the child. In this case, A is parent of C and C is a child of A. Nodes that can be reached from other nodes are called descendants. Nodes that lead to a path to a specific node are called. This is how a Bayesian network performs. For example, C and E are descendants of A, and A and C are ancestors of E. There are no loops in Bayesian networks since no child can be its own ancestor or descendant. So it's a clear demarcation. There are no loops. Bayesian networks will generally also include a set of probability tables, that are CPTs, stating the probabilities for the true false values of the variables. The main point of Bayesian network is to allow for probabilistic inference to be performed. This means that the probability of each value and of a node in the Bayesian network can be computed when the values of the other variables are known. Also because independence among the variables is easy to recognize since conditional relationships are clearly defined by a graph edge. Not all joint probabilities in the Bayesian system need to be calculated. So that's how it works. Now other question, Bayesian network consists of how many parts? It's a very simple question, only two parts, that is the graph and the CPT, conditional probability table. So Bayesian network consists of two parts: directed acyclic graph, that is, there are no cycles as we have seen, directed acyclic graph, and table of conditional probabilities, that is CPT, conditional probability table. That's a very important part of Bayesian network. Like, see, this is the Bayesian network. As a very famous problem which has been studied in the Bayesian network, that there one person has put an alarm. Okay, this problem is very important. That alarm buzzes when burglary happens. Basically, he wants to stop burglary at his home. He has gone some outside place. So when alarm will raise, but this alarm can also buzz if earthquake occurs. So due to earthquake, which probability is very less, then also alarm will happen. Otherwise burglary will happen, then alarm will happen. But if this alarm happens, then John is a nearby, his neighbor, he will listen and he will call the person that there is alarm at your home, means burglary has happened, or earthquake is very less probable. And then if Mary also calls, there is another of his friend, she also calls if alarm has happened. He has told two people that if you listen the alarm, you tell me. So now you see, this is the graph, how it is described, Bayesian network graph, acyclic graph, and then these are the CPTs, conditional probability tables. So this is how Bayesian network is defined. Now, a hybrid Bayesian network may consist of discrete variables only, discontinuous variables only, both discrete and continuous variables only. Hybrid Bayesian network means it's a hybrid. It will consist of discrete variables also and continuous variables also. That's the definition of a hybrid Bayesian network. So both discrete and continuous variables, C is the answer. The hybrid Bayesian network contains both discrete and continuous variables as the numerical inputs. To define the hybrid network, both kinds of distributions are used at wide probability distribution. Now coming to this question, very important question again. Consider a Bayes net with the following graph. This is the graph. A that leads to B, C, D, E, and B, C, D leads to F, E, gentlemen, and G. The factors associated with the Bayes net are PA, PB over A, PC over PA, and then PB over A, PC over A, PD over A, then PE over A connected, then PF over BCD, F over BCD is not there, and PG over F. We will consider variable elimination to answer the query PG over plus E, something like this. Now, if we eliminate variable A, we are eliminating variable A, what is the resulting factor as a function of original factors? So here you see, we have got four options. Since we have eliminated variable A, so variable A can't be there in that function FCD. So A can't be the answer. A we can remove straight away. Now B or C, one we have to choose. Now F, B, C, D, G, but G can't be taken because G we have to take actually G is plus E, so plus E will be taken, and then PA, PB, PA, PB over A, then PC over A. This is the correct way of defining this thing. PF over BCD, that doesn't mean F over BCD is not the right way to do. F over BCD, PG over F. So this is the right answer actually. PA, PB over A, PC over A, PD over A, P plus E over A, because E has already been replaced by plus C, and E has to be taken into consideration. So that's how the answer is C, that is F of BCD plus E is equal to sigma A, PA, PB, PB over A, PC over A, PD over A, P plus E over A, because we have already done that how this is dependent. Thank you.